In previous sessions, we had gone through with topics related with antenna theory and measurement. Electricity flowing along metal conductor creates invisible electromagnetic waves in the form of radio waves. These waves, partly electric and partly magnetic, travel out at the speed of light and carries signals with them. The wave propagates through a medium, the air. Now, what happens when the radio wave meets a hard surface like a wall, or enters a new medium, or moves around an obstacle, or meets another wave? Do the waves remain the same? Does this situation affect the signal carried by these waves? These are the conditions that we will look into this session, radio propagation, another topic of BEE 4433 antenna theory and propagation. In a wireless communication system, electromagnetic waves carry signals and travels with the speed of light. The electric field and magnetic field determine the polarization of the waves. In general, there are three mediums for radio wave propagation, namely ground wave, sky wave, and space wave. Let's look into the ground wave properties medium. Also known as surface wave, it typically caters up to 2 MHz transmission, which means the strongest at low frequency and low and medium frequency range. For example, the AM radio. It follows the curvature of Earth and could travel beyond horizon. The antennas adopted for the communication system are vertically polarized antennas. The ground waves is unaffected by changing condition of the atmosphere. This means, given enough power, the communication system can communicate between any 2 points on Earth. However, this comes with a trade-off as it requires high transmission power, and the surface wave is attenuated by dielectric losses on Earth's surface. Also, it requires large antennas due to its operational at low to medium frequency range. Another medium is the sky wave. In this medium, signal reflected from ionized layer of atmosphere back down to Earth. Signal travels in a number of hops and reflection effect that is caused by refraction. The ionosphere is approximately about 50 to 400 kilometers above the Earth's surface. Examples include radio amateur and citizen band CB radio. The space wave propagation medium houses energy that travels in the lower few miles of the atmosphere. There are two types of sky wave propagation. Type 1 is known as direct wave, in which propagation travels in the line of sight. This path, however, is limited by the curvature of Earth. The waves are deviated and cannot travel beyond horizon or obstacles. This kind of communication link is suitable for ultra-high frequency or very high frequency or microwave signals. Type 2 is the indirect or ground reflected wave, in which the waves are waves that is being reflected by the Earth's surface as they propagate between the transmit and receive antennas. Space wave propagation mode is used for propagation of very high frequencies such as the Ku band satellite television. The sky contains ionospheric layer that absorb large quantities of the sun radiant energy and ionize the air molecules, creating free electron. The three layers of the sky waves are D layer. It is approximately between 50 to 100 km above the Earth's surface. This layer has little ionization. It has a very little effect on the direction of the propagation of radio waves. The amount of ionization in D layer depends on the altitude of the sun above horizon. This layer disappears at night. The D layer region, the very low frequency and the low frequency waves are reflected. However, the high frequency and the medium frequency waves are absorbed. The E layer is 100 to 150 km above Earth's surface. The maximum density is approximately 70 miles during noon, when the sun is at its highest point. This layer totally disappears at night. The E layer aids medium frequency surface wave propagation while reflects higher frequency waves during daytime. The next layer is the F layer. F layer consists of F1 and F2 layers. During daytime, the F1 layer is located approximately around 140 to 150 km above the Earth's surface, while the F2 layers is approximately between 140 to 300 kilometers. During night, the F1 layer combines with the F2 layer to form a single layer. The F1 layer absorbs and attenuates some high-frequency waves, although most of the waves pass through to the F2 layer where they will reflect back to Earth. Next is the space wave medium. Total distance covered by the propagation path depends on the height of the antenna. When the antenna is above sea level, the equation is as follows. A phenomenon that is related to the space wave medium is dark propagation. It is a condition at atmospheric propagation in which it happens in Earth's lower atmosphere. Vertical refraction index is such that the electromagnetic wave, radio wave and light are refracted and reflected against layers or less density above and are guided to follow the curvature of Earth. Let's delve into the details of propagation mechanism. Reflection occurs when a wave impacts an object that is having larger dimension than the wavelength. During reflection, part of the wave may be transmitted into the object with which the wave has collided. The remainder of the wave may be reflected back into the medium through which the wave was originally traveling. Example of this situation is the surface of Earth. In an indoor environment, objects such as walls and floors can cause reflection. When the path between transmitter and receiver is obstructed by a surface with a sharp irregularities, the transmitted waves undergo diffraction. Diffraction allows wave to bend around the obstacle even when there is no line of sight path between the transmitter and receiver. For example, objects in an indoor environment which can cause diffractions include furniture and large appliances, whereas in an outdoor environment, diffraction can be caused by buildings. The third mechanism which contributes to electromagnetic wave propagation is scattering. Scattering occurs when the wave propagates through a medium in which there are a large numbers of objects with dimensions smaller than the wavelength. In an indoor environment, objects such as plants and small appliances can cause scattering, whereas in an outdoor environment, scattering can be caused by rough terrain of the ground. Another mechanism is refraction. Refraction is the change of direction of wave passing from one medium to another or from a gradual change in the medium. Refraction of light is the most commonly observed phenomenon, but other waves such as sounds and radio frequency waves also experience refraction. It is accompanied by a change in the speed and wavelength of the waves. The combined effect of reflection, diffraction, and scattering cause multipath. Multipath happens when the transmitted signal arrives at the receiver by more than one path. The multipath signal components combine at the receiver to form a distorted version of the transmitted waveform. The multipath components can combine constructively or deconstructively depending on the phase variations of the component signals. The destructive combination of the multipath components can result in a severely attenuated received signal. Once the propagation medium is identified, the next stage is to determine appropriate radio propagation model for the system. A radio propagation model, which is an empirical mathematical formulation for the characterization of radio wave propagation, as a function of frequency, distance, and other conditions. Various models were derived depends on the environment, such as indoor or in a confined area, outdoor, urban, and free space. Propagation models are tools used for predicting the average signal strength at a given distance from the transmitter, or estimating the variability of the signal strength in a close spatial proximity to a particular. Conceptually, these propagation models is derived based on three principles, which are empirical models, that is based on measurements linked to the environment. It is simple as the empirical models acquire only few parameters. It uses statistical properties. However, it is not very accurate. Deterministic models, on the other hand, are based on fixed geometry such as buildings and streets. The deterministic models are used to analyze site-specific environment, hence require enormous number of geometry information about the city. Deterministic models come with a heavy computational effort, which results in accurate propagation models. And finally, a combination of both techniques, which is known as the semi-deterministic models. In this session, we will look into indoor propagation model, outdoor propagation model, and space propagation model. Indoor propagation model is a radio propagation model that estimates the path loss inside a room or a closed area limited by walls of any form. An indoor radio channel, the distance covered are much smaller. However, the variability of the environment is significant. The indoor radio channel depends heavily on the factors which include building structure, layout of rooms, and the type of construction materials used. These factors are affecting the electromagnetic wave propagation in terms of reflection, diffraction, and scattering. Several established indoor propagation model includes long-distance path loss models, which assumes that path loss varies exponentially with the distance. Log normal shadowing, that takes into consideration of shadowing effect that can be caused by varying degrees of clutter between the transmitter and receiver. Addition to attenuation factors for log distance model. This technique is an attempt to modify the log distance model by including additional attenuation factors based on measured data. The attenuation factor model incorporates a specific path loss exponent and for attenuation factors to provide an estimate of indoor path loss. An additive path loss model. An additional path loss model which has been investigated by researchers is an additive path loss model. In this model, individual losses caused by obstructions between transmitters and receivers are estimated and then added together. Example of indoor propagation model is home, shopping mall, and office building. The outdoor propagation model is a systematic interpretation measured of data obtained in a specific area. Outdoor radio transmissions take place over an irregular terrain. The terrain profile must be taken into consideration for estimating the path loss. Trees, buildings, and hills must be taken into consideration. Examples of this model include Longley-Rice, Durkin's model, Okumura models, Hatta models, and wideband PCS microcell. The free space propagation model assumes a transmit antenna and receive antenna to be located in an otherwise empty environment. Neither absorbing obstacles nor reflecting surface are considered. In particular, the influence of the Earth's surface is assumed to be entirely absent. An example of free space propagation model is prediction of received signal strength when the transmitter and receiver have direct line of sight, such as in a satellite communication link between a satellite and also ground station. The free space path loss formula derives from the Friis transformation formula. This states that In a radio system consisting of a transmitting antenna, transmitting radio waves to a receiving antenna, the received power received is being influenced by the directivity of the received and transmitting antenna, the signal wavelength, and the distance between the antennas. Path loss is a concept in radio communications, refers to the phenomenon of the power density decrease of an electromagnetic wave as it propagates through space. Path loss is a determining factor in analyzing the link budget and counting of all gains and losses from the transmitter to the receiver through a particular medium of a communication system. Path loss can be caused by various factors such as refraction, diffraction, free space loss, aperture medium coupling loss, or absorption. Other variables in determining the path loss are environment, the type of terrain, the medium of propagation, the distance between emitter and the receiver, and the type of mounting of the antennas. Multipath is another effect that is related to path loss. Link budget takes into consideration all the gains and losses from the transmitter to receiver, from path losses, antennas feeders, power levels, and receiver sensitivity. It is a key element in designing a mobile network and ultimately leads to a network design that functions correctly according to all requirements at a reasonable cost. Link budget is influenced by received and transmitted power, gains, and losses. The factors that determine link budget can vary in time, as path loss does, and such cases, the worst case scenario will be taken into consideration. This figure is an example of a link budget between a transmitting tower and a cellular phone. In wireless communication, fading is a variation of the attenuation of a signal wave with various variables. These variables include time, geographical position, radio frequency. Fading is often modeled as a random process. A fading channel is a communication channel that experiences fading. In wireless system, fading may be due to multipath propagation, weather, or shadowing from obstacle affecting the wave propagation, sometimes referred to as shadow fading. Types of fading in wireless communication system are shown in the figure here. Large-scale fading occurs when an obstacle comes in between the transmitter and receiver. This interference type causes significant amounts of signal strength reduction. This is because electromagnetic wave is shadowed or blocked by the obstacle. It is related to large fluctuation of the signals over distance. There are two clusters that causes large fading, which are path loss and shadowing. Shadowing is a deviation of received electromagnetic power from average value. It is results of obstacles over path between transmitter and receiver. It depends on geographical position as well as radio frequency of electromagnetic waves. Small-scale fading is concerned with rapid fluctuations of received signal strength over very short distance and short time period. It is divided into two main categories, namely multipath delay spread, and Doppler spread. Based on multipath delay spread, there are two types of small-scale fading, which are categorized as flat fading and frequency selective fading. The wireless channel is said to be flat fading if it has constant gain and linear phase response over bandwidth. On the other hand, frequency selective affects different spectral components of a radio signal with different amplitudes. The multipulse fading types depends on propagation environment. Doppler spread can further be divided into fast fading and slow fading. The phenomenon of fast fading is represented by rapid fluctuations of signals over small area, for example bandwidth. When the signals arrive from all directions in the plane, fast fading will be observed for all directions of motions. Fast fading occurs when channel impulse response changes very rapidly within the symbol duration, whereas slow fading is results of shadowing of buildings, hills, mountains, other objects over the path. If the wireless device is moving, there are changes in the scattering environment. The spatial variations in the amplitude and phase of the composite received signals are having time variations. This is a phenomenon that is termed as envelope fading. The time rate of envelope fading depends on the velocity of the wireless device. Absorption is when a wave comes into contact with a medium and causes the medium molecules to vibrate and moves. The vibrations absorb or take some of the energy away from the waves and less of the energy is reflected. The reduction in power density due to the non-free space propagation is called absorption. Absorption of radio frequencies in a normal atmosphere depends on the frequency and is relatively significant below approximately 10 GHz. Attenuation is a general term that refers to any reductions in the signal strength. Attenuation occurs with any type of signals, whether digital or analog. Sometimes called loss, attenuation is a natural consequence of signal transmission over long distance. Waves spread out or disperse over a large area, decreasing the power density. The attenuation is due to the spherical spreading of the waves. It is sometimes called space wave attenuation of the wave. Another property that is related to electromagnetic waves is the wave front. The wave at each point varies sinusoidally in time with a single temporal frequency. Otherwise, the phase is not well defined. Wave fronts usually move with time. For waves propagating in unidimensional medium, the wave front is usually a single point, whereas in a two-dimensional medium, there are curves, and in three-dimensional, there are surfaces. A wave front is formed when points of equal phase on rays propagated from a same source are joined together, as shown here. A wavefront shows a surface of a constant phase of a wave. The closer to the source, the more complicated the wavefront becomes. When a surface is plane, its wavefront is perpendicular to the direction of the propagation. Radio noise is an unwanted random electrical signals, fluctuating voltage, which always presents in the radio receiver in addition to the desired radio signals. Throughout these sessions, we look into wave propagations and its properties. Radio propagations is influenced by the behavior of radio waves as they propagate from one point to another point into various parts of the atmosphere.